Hi everyone. Today I'm going to talk about the potential role of intrinsic charm. That is, if we try to introduce an intrinsic charm to nucleons, what happens to atmospheric lepton fluxes, or how much intrinsic charm can we introduce, if we can introduce intrinsic charm at all or not. So I'll just quickly go over this. Atmospheric leptons are very interesting on their own because we can probe BSM physics through high energy PP collision or high energy PER collisions. We can learn more about hadronic interaction at very high energies. They also provide an interesting background to astrophysical neutrinos. So understanding atmospheric leptons is of significant importance for us. Atmospheric leptons. In this talk, I'll be mostly talking about muons and muon neutrinos. They are produced by cosmic ray particles interacting in the Earth's atmosphere with air nucleus. So we have high energy nuclear and air collisions, which can produce a myriad of secondary particles, which can further decay into final state leptons and their corresponding lepton neutrinos. We can have secondary particles like kaons, pions produced, which can have weak decays to muons, muon neutrinos. We can have charm hadrons, which are produced, and they can also produce corresponding leptons and lepton neutrinos. For all the flux calculations here, we'll be using MCQ in order to simulate the results. For the interaction model, we'll be using Sybil 23C, and the primary cosmic ray flux model that we'll be using is the H3A flux model from Hiller-Geiser. So as I said, atmospheric leptons are its flux can be divided into two categories. One is the conventional part, and another one is the prompt part. I'll be mostly talking about muons and muon neutrinos. So for muon neutrinos, we have a conventional part, which is the weak decay of pions and kaons, and a prompt part, which is mostly from perturbative QCD or from the decay of charm hadrons. For muons, we have a conventional part, a perturbative QCD part, but we also have an additional unflavored part, which is from the electromagnetic decay of unflavored mesons to muon pairs. For example, we have eta meson, which can decay to a mu plus mu minus pair along with a gamma. We try to look at the current measurements from IceCube for atmospheric muons. For atmospheric muons, in the left-hand side, we have the angle average muon flux up to a zenith angle of 60 degrees, along with the beam by beam error bars. And on the right-hand side, we have an upper limit to the prompt muon neutrino. We only have an upper limit because at this energy range, the atmospheric neutrino flux is mostly dominated by the conventional part. So they can set only an upper limit depending on the model that they use. For the upper limit that we have shown here, it's based on the ERS model used for the hadronic interactions. If we go back to the previous plot, there is some deficit in the calculated flux given by the orange line in the left-hand plot and compared to the data shown by the black dots. So how can we answer for this discrepancy? We'll try to introduce intrinsic charm in this case. So intrinsic charm are just non-perturbative fluctuations to the nucleons. So because of non-perturbative fluctuations, we can decompose the nucleon Fock state into two parts. We can have the conventional 3-quark Fock state and a 5-quark Fock state containing CC bar contributions, which have a small but non-negligible weight. Because of this additional CC bar contributions in the Fock state, they can these fluctuations can give rise to hadronization when we have nuclear and air collisions, and this hadronization can give rise to the enhancement to the production of charm hadrons. So we can have enhancement to the production of D0 bar, lambda C, and D minus when we have the nucleons colliding with the air nucleus. in order to look into the enhancement, we need to know about the differential cross-section of the intrinsic charm production. So differential cross-section of the charm hadrons produced by this intrinsic charm fluctuations. So the differential cross-section depends on three different parameters. So we have the intrinsic charm fragmentation functions, which are the momentum fragmentation functions. We have a WC intrinsic, which is just a normalization to the differential cross-section, and we have a P air inelastic cross-section. So the WC intrinsic consists of two parts. One is the non-negligible weight of the 5 quark Fock state that we discussed. And the second part is the probability of the intrinsic charm hadronizing to final state charmed hadrons. We can use various different intrinsic charm models. The model that we'll be looking at today is going to be a model based on Regge trajectories, for which we have the intrinsic charm fragmentation function given by the following equation. And here the A psi and AN are the intercepts of the J psi meson and baryons and nucleon intercepts of the meson and baryon trajectories in the Regge theory. So for our results, we mainly use A psi equals to -2 and AN equals to minus 0.5. We also assume that the momentum fraction at which the D0 and D minus mesons will be produced is 1 minus x of the momentum fraction where the lambda c hadrons, lambda c baryons are produced. So the following plot shows the intrinsic charm fragmentation functions for the production of D0 bar and lambda c for the model that we are using. So these are the results for the inclusion of intrinsic charm. So we can try to include intrinsic charm and try to find out the amount of intrinsic charm that we need in order to answer for the deficit of the theory predictions and the calculated and observed muon flux. So if we try to do that, we see that the amount of intrinsic charm needed or the normalization of the intrinsic charm that we need is very small, which is 3.9 times 10 to the power minus 3. We can see that this is indeed the best fit for the amount of normalization that we need, because we can see when we add intrinsic charm, the ratio of the data compared to the total theory prediction comes very close to 1. But on the right-hand side plot, in the bottom part, we can also see that if we have no intrinsic charm or WC equals to 0, we still see that the theory prediction still goes through the large error bars that we have in the data. So large error bars in the higher energy data makes it hard for us to make a conclusive statement about the role of intrinsic charm. However, we can also look at the neutrino spectrum and see whether this amount of intrinsic charm is required or not. So if you look at the neutrinos spectrum or the prompt neutrino spectrum, we see that if we include an intrinsic charm contribution with a normalization of 3.9 times 10 to the power minus 3, we exceed the prompt neutrino upper bound that is set by IceCube. So we should not be able to incorporate this much amount of intrinsic charm. So we must try to add the amount of intrinsic charm such that we do not exceed the upper limit, but we try to saturate the upper limit set by IceCube. So if we try to do that, we find the normalization to be 4.4 times 10 to the power minus 4, which is 10 times less than the normalization that we found in the case of muons. So, but what happens to the data or what happens to the muons? We see that there is still some discrepancy in the observed of data and the theory predictions. How can we try to resolve this discrepancy? We saw that in the case of atmospheric muons, there is one component to the total muon flux, which is the unflavored contribution, which is not there in the case of muon neutrinos. So we can try to, and there are a large amount of uncertainties in the calculation of unflavored flux. So we can try to rescale the unflavored contribution to the muon data. So we can try to rescale the unflavored contribution. Let's say we have an intrinsic charm with a normalization such that we saturate the upper bound to the prompt neutrinos, and we try to rescale the unflavored contribution. We find a scaling of 4.39. That means we need to multiply the total unflavored flux by a factor of 4.39. But as we saw in the case of intrinsic charm, there is high amount of uncertainties in the higher energy data in the case of muons. So making conclusive statement about intrinsic charm is very hard. So we can have no intrinsic charm and still try to rescale the unflavored contribution. So if we try to do that, we find a scaling factor of 4.84. So this shows that the scaling factor for the unflavored contribution is not that much different if we have some intrinsic charm or if we have no intrinsic charm. So again, it shows that making a conclusive statement about intrinsic charm is hard based on the data that we have till now. We can use different models of intrinsic charm. We show the preliminary results for the 3 models that we can consider for intrinsic charm contribution. This table shows us the amount of intrinsic charm normalization that we need when we try to fix the muon data. But in every case, we always exceed the neutrino upper limit set by Skill. So we have to consider less amount of intrinsic charm, and then in order to still incorporate or answer for the discrepancy in the muon data, we have to rescale the unflavored contribution. So in every case, we have to rescale the unflavored contribution by a factor of 4.4-ish. This is the summary. I'm running out of time, so I'll just leave it over here so that you can ask any questions you have. So let's.
Is there a pressing question? Because we're running out of time. So if there's a pressing question, we can have one. Otherwise, we can proceed to the next speaker.
Very quick question. The ice cube data on the muons, do you recall what year that was?
It was 2016. We asked
2016.
Yeah,
okay, so this is a quite old measurement.
Yeah, quite old measurement. Yeah.
Okay, so let's thank again.